Now we will look upon the characteristics of a reversible process. Okay. Now understanding these characteristics is essential for grasping how idealized process can be modeled and their significance in energy systems. So first we will start with equilibrium. One of the defining characteristics of a reversible process is that the system remains in equilibrium with its surrounding throughout the entire process. This means that at every stage, the system properties such as pressure and temperature are uniform and balanced with those of the environment. Now here, the implications of equilibrium include it can be returned to its original state without any change to the surrounding. So next we will see the important characteristics for an reversible process is infinitesimal changes. Reversible process occur through infinitesimal changes in external parameters such as pressure or temperature. These small changes ensure that the system remains close to equilibrium at all times. When expanding a gas reversibly, the volume can be increased by tiny increments, allowing the system to adjust gradually without significant deviation from equilibrium. Now, in reversible process, there is no energy loss as heat due to friction or other dissipative effects. This characteristics means all the energy input into the system can be converted into useful work. Now here, the absence of dissipative effects allows for maximum efficiency in energy transformation. Next important point is a constant entropy. During a reversible process, the total entropy of the system and its surrounding remains constant. This characteristics aligns with the idea that reversible processes are idealized scenarios where no entropy is generated. Since there is no increase in entropy, these processes are often referred to as ideal because they do not occur naturally in real world conditions. Now, if you check the work output of a reversible process, this reversible process yields the maximum possible work for a given change in state. Because no energy is wasted and all transformations are efficient, reversible process represents the upper limit of work output from a thermodynamic cycle. In an idealized scenario, a reversible heat engine operating between two temperature reservoirs can extract maximum work from heat input while minimizing the waste. Now the examples of reversible process is isothermal expansion of a ideal gas. This is a classic example. As the gas expands slowly while maintaining a constant temperature, and that are called as isothermal conditions. The process occurs through infinitesimal changes in volume and pressure. The gas remains in equilibrium with its surrounding throughout the expansion. No heat is lost due to friction or other dissipative effects. The total entropy change for the system and the surrounding remains constant during this idealized expansion. This expansion or these examples illustrates how reversible process can be modeled to maximize efficiency and work output. Thus, reversible processes are characterized by equilibrium with the surrounding, infinitesimal changes, or no energy dissipation, constant entropy, and maximum work output. While this process serves as an ideal model for undertaking thermodynamics, it's important to remember that real-world processes are typically irreversible due to inherent efficiencies, that is, inefficiencies. Okay. Now we are going to see characteristics of irreversible process. Understanding these characteristics is essential for grasping how energy transformations occur in a real-world systems and their implications for efficiency. One of the defining characteristics of an irreversible process is that the system is not in equilibrium with its surrounding during the process. This lack of equilibrium means that there are gradients such as temperature or pressure differences that drive the process forwards. Because the system is not at equilibrium, it cannot return to its original state without external intervention. Also, this irreversible process involves finite changes in external parameters such as pressure, volume, or temperature. These changes are typically rapid and significant, leading to a departure from equilibrium. When a gas expands rapidly into a vacuum, the change in volume occurs quickly and results in a non-uniform distribution of gas particles. In reversible process, energy is lost as heat due to friction or other dissipative effects. This dissipation leads to an increase in entropy and signifies that not all the energy can be converted into useful work. The presence of dissipative effects means that some energy is irretrievably lost to the surrounding, reducing the overall efficiency. Another the key characteristics of the reversible process is that the total entropy of the system and its surrounding always increase. This increase aligns with the second law of thermodynamics, which states that natural processes tend to lead to a greater disorder. The increase in entropy reflects the irreversibility of the process Once it occurs, it cannot simply be reversed without additional work or energy input. Irreversible process yield less work than reversible process for the same change in the state, because some energy is dissipated as heat and not all input energy can be converted into work. The efficiency of this process is inherently lower. In the real engine cycle, losses due to friction and heat transfer reduce the amount of useful work produced compared to an idealized reversible cycle. Now let's look certain common example of irreversible processes. The first one, we can say there is a juice expansion. When a gas expands into a vacuum, it does so rapidly without doing any work on the environment. The internal energy remains constant, but the process cannot be reversed without additional energy input. Next process is the heat transfer through a finite temperature difference. Heat flow spontaneously from hot to cold regions, increasing entropy in the process. This transfer cannot be reversed without external work being done. Next important parameter for the irreversible process is the frictional losses. When two surfaces slide against each other, friction generates heat and dissipates energy, leading to increased entropy and irreversible changes. Next is the spontaneous mixing process. When two different substances, take an example of a dye and a water, when they are mixed, they are spontaneously mixed, and this process is irreversible due to increase in entropy, which we have seen in previous lecture. Thus, irreversible processes are characterized by non-equilibrium conditions that are finite changes in parameters, energy dissipation, and an increase in total entropy and reduced work output compared to a reversible process. These characteristics highlights the challenges the engineers face when designing efficient systems and understanding natural phenomena. Now, we will explore certain key examples of a reversible process in thermodynamics. While these processes are idealizations and rarely occur in nature, they provide valuable insights into the principles of thermodynamics and the maximum efficiencies that can be achieved. So first, take the example of an isothermal expansion. In this process, the ideal gas expands slowly at a constant temperature. The system remains in equilibrium with its surrounding throughout the expansion. As the gas expands, it absorbs heat from the surrounding to maintain its temperature, allowing it to do work on its environment. The process is carried out infinitely slow, ensuring that the system is always in equilibrium. The entropy change for the gas can be calculated using the formula delta S is equal to Q reversible divided by temperature. Now next is the adiabatic compression. In this process, the gas is compressed slowly without any heat transfer or to form the surrounding, or there is no any heat loss to the surrounding. And this process, we say that it is a adiabatic process. Since the compression occurs so gradually that the gas remains in thermal equilibrium with itself throughout the process. Now, as the gas is compressed, its internal energy increases, which raises its temperature. Since there is no heat exchange, all the work done on the gas results in an increase in internal energy. In a reversible adiabatic process, the entropy remains constant because there are no dissipative effects. Next is the Carnot cycles. The Carnot cycle represents the theoretical model that demonstrates maximum efficiency for a heat engines. It consists of 4 reversible processes. The 2 are isothermal, that is one for the heat absorption and the other for the heat rejections. And there are the 2 adiabatic processes, one for the expansion and one for the compressions. The Carnot cycle operates between 2 temperature reservoirs, absorbing heat from the hot reservoir and rejecting waste heat to the cold reservoirs. The efficiency of the Carnot engine is given by 1 minus T cold divided by T hot, where T cold represents temperature of the cold reservoir and T hot represents temperature of hot reservoirs. The Carnot cycle serves as an ideal benchmark for real-world engine, illustrating the upper limit of the efficiency. Now, no process can be perfectly reversible due to inherent dissipative effects, that is friction and turbulence. Real systems experience certain irreversibilities that lead to energy losses and increased entropy. Now, in case of a reversible process, the entropy changes are also reversible. This means that if you return the system to its initial state after undergoing a reversible process, there will be no increase in the entropy for the system and its surrounding. This characteristic differentiates a reversible process from irreversible ones where the total entropy always increases. Thus, the isothermal expansion, adiabatic compression, and the Carnot cycle illustrates the key concept of a reversible process in thermodynamics. While these processes serve as ideal models for understanding the energy efficiency and transformation, real-world application must account for the irreversibilities and the energy losses. Now we will see certain examples of an irreversible process. These processes are essential for understanding how energy transformation occurs in the real world, and this illustrates the concept of entropy increase. Okay, the first one we will see, that is the Joule's expansion. Okay, in this process the gas expands into a vacuum. In this process the gas expands into a vacuum without doing work on the surrounding. This expansion occurs spontaneously and is characterized by a rapid change in the volume. Since there is no opposing pressure, the gas expands freely and there is no heat exchange with the environment. This process is irreversible because once the gas has expanded into the vacuum, it cannot return to its original state without external work. Next is the heat transfer. Heat naturally flows from a hot body to cold body until thermal equilibrium is reached. This process occurs spontaneously and is driven by the temperature difference between the two bodies. The transfer of heat increases the total entropy of the system and its surrounding. Once heat has flowed from the hot to cold, it cannot spontaneously flow back without external interventions. Next common example is the friction. When two surfaces slide against each other, mechanical energy is converted into heat due to frictional forces. This conversion results in energy dissipation and an increase in entropy. The key points here include the heat generated from the friction cannot be fully recovered as a useful work. This process is such that it tells us how mechanical energy losses contributes to irreversibilities. And next important point is the mixing of these gases. As we know, when two different gases are allowed to mix, such as helium and nitrogen, they do spontaneously mix. The molecules of each gas distribute themselves throughout the available volume, leading to the increased disorders. Once they are mixed, the gases will not spontaneously separate back to their original state. This spontaneous mixing results in an increase in total entropy due to greater number of possible microstates. Now, all this irreversible process results into increase in total entropy. According to the second law of thermodynamics, natural processes tends to lead to greater disorders. The increase in entropy reflects the inherent irreversibility of this process. Now we will see the examples of certain process in nature, such as melting of ice. When ice melts into the water, it undergoes a spontaneous change that increases the entropy as the molecule order decreases. Burning of the wood. Now, the combustion transforms the solid wood into ash, gases, and heat, resulting in a significant increase in entropy as the energy disperses. Rusting of iron, as we all know, the oxidation of the iron leads to rust formation, which represents a spontaneous process that increases the disorder and the total entropy over time. Now, these examples such as Joule's expansion, heat transfer, friction, and mixing of the gases illustrates key concepts of irreversible process in thermodynamics. This process demonstrates how energy transformation are inherently insufficient due to dissipative effects and always lead to increase in the total entropy. Now we will see the comparison of reversible and irreversible process. Understanding this is very much crucial for grasping how energy transformation occurs. Now, as we all know, the changes in these two processes, for example, in reversible process, it is an infinitesimal changes, but in case of irreversible process, there are finite changes. There is no dissipation in case of reversible process, but there is certain dissipation of energy in case of irreversible process. The entropy in case of reversible is constant, but in case of irreversible process, the entropy increases. Maximum work output is achieved in case of this reversible process, and there is a less output as compared to that of reversible process in case of this irreversible. Now, reversible process can be reversed, but this irreversible process cannot be reversed. Okay. Now, as we all know, reversible and irreversible process, this exhibits distinct characteristics that define their behavior in thermodynamics. Reversible processes are ideal processes that maximize efficiency and maintain constant entropy, while irreversible processes are common in nature, characterized by finite changes, energy dissipation, and inevitable increase in entropy. Now, coming on to the importance of this reversible process, okay, these are important as a theoretical model. As we know, reversible process are ideal process having the maximum efficiency. Okay, in context of this heat engine, reversible process helps to establish the Carnot efficiency, which is the highest possible efficiency for any engine operating between the two temperature reservoirs. Now, engineers utilize the principle of reversible process to design more efficient energy systems. By minimizing the entropy productions, they can approach the ideal efficiencies predicted by the reversible models. For example, in designing the thermal systems like heat exchangers or engines, engineers aim to approximate reversible conditions to maximize energy convergence and minimize waste. Now, the Carnot cycle, as we all know, is a theoretical cycle that denotes the maximum efficiency of a heat engine operating between two temperatures. It consists of two isothermal and two adiabatic processes, all of which are reversible. The Carnot cycles serve as a standard for evaluating the performance of real heat engines, guiding improvement in designs and operations. Now, in case of the diesel engines, which achieve higher efficiency by approximating reversible combustion conditions, by optimizing compression ratios and minimizing the heat losses, these engines can operate closer to that of an ideal behavior described by the reversible process. Now, the optimization results in the better fuel economy and reduce emissions compared to that of less efficient engines. Now, minimizing this entropy production is also key to achieving the higher efficiency in thermodynamic systems. Reversible processes, by definition, do not produce the entropy, making them as an essential reference point for understanding how to reduce losses in the real applications. Now, by striving to design processes that minimize entropy generations, engineers can enhance the system performance and sustainability. Now, therefore, these reversible processes are vital for understanding the thermodynamic principles and setting the benchmarks for efficiency in engineering applications. They inform the design and optimization of the systems across various fields, from power generation to refrigeration, ultimately leading to more efficient and sustainable technologies. Now we will see the impact of irreversible process. Irreversible process play a significant role in thermodynamics and have far-reaching implications for the energy efficiency and environmental impact. Let's explore the key aspect of these processes. So first is the energy loss. As the irreversible process result in the energy loss as a heat, which reduces the overall efficiency of systems. During this process, some energy is dissipated due to friction, turbulence, and other factors, meaning that not all the input energy can be converted into useful work. Take an example of power plants, where the energy generated from burning fuel is partially lost as a waste heat, leading to lower efficiency in electricity productions. Next is the environmental impact. The increased entropy production associated with the irreversible process contributes to the environmental degradations. As the energy is lost and the system becomes less efficient, more resources are needed to achieve the same output, leading to greater environmental strain. Understanding the entropy changes in this process helps to assess their environmental impact and encourage the development of more sustainable practices. Now, there are certain examples of this irreversible process, such as the power plants. They generate a significant amount of waste heat during electricity productions, which cannot be fully recovered. In case of this vehicle, the internal combustion engines convert the chemical energy from the fuel into mechanical work, but lose a substantial portion of that energy as heat due to friction and exhaust. Next is the heat transfer. Heat flows spontaneously from hot bodies to the cold bodies, resulting in increased entropy and irreversible changes. Next is for the mixing of gases. When different gases mix, they do spontaneously mix and cannot be separated back into their original state without any external work. Now, there are certain strategies which are associated to reduce these inefficiencies with the irreversible process. First one is improving the system design. Engineers can design systems that minimize the dissipative effects such as frictions and turbulence, thereby reducing the energy loss. Enhancing the insulations in thermal systems. Better insulation can minimize the heat loss during energy transfer process. Third is the implementing efficient technologies. Utilizing advanced technologies such as combined cycle power plants or regenerative braking in the vehicles can help to recover and reduce the lost energy. And finally, the role of entropy. Understanding the entropy changes is very much crucial for assessing the environmental impacts of the irreversible process, since this process inherently leads to an increase in the total entropy. By analyzing how much entropy is generated during various operations, engineers and scientists can identify the opportunities for improvement. This understanding can guide the development of more efficient systems that aligns with the sustainability goals. Therefore, these irreversible processes are characterized by energy loss, increased entropy production, and significant environmental impacts. By recognizing these characteristics and implementing mitigation strategies, we can improve system efficiency and reduce our ecological footprints. Understanding the role of entropy in this process is essential for developing sustainable technologies and practice. Now, we will discuss the interplay between biological and chemical processes, focusing on their irreversible nature and the implication for entropy and energy transformations. Many biological processes once thought to be irreversible now are now understood as a pair of irreversible processes. This shift in understanding highlights the complexity of biological systems and their reliance on the thermodynamic principles. Metabolic pathways consist of a series of enzymatic reactions that converts substrates into products. Each step in these pathways is often irreversible, contributing to the overall directionality of metabolism. Next is the chemical reactions. The spontaneous chemical reactions are typically irreversible without external energy input. Once reactants are transformed into products, the process cannot simplify to be reversed under normal conditions. The irreversibility is important for understanding reaction kinetics and thermodynamics, as it signifies that energy must be supplied to reverse the reactions. Now we will see the impact of enzymes and irreversible reactions. Enzymes play a crucial role in catalyzing reactions between biological systems. Many enzymes facilitate irreversible reactions, which are essential for driving metabolic process forward. The enzymes catalyzes the, we can say, different glucoses, okay, and which is an irreversible process that commits glucose into further metabolism. Now there are certain metabolism pathways. The metabolic pathways involve a series of irreversible steps that converts the substrates into energy or the building blocks for the cellular functions. Each irreversible step helps to maintain the directionality of metabolic process. The irreversibility of the step is crucial for maintaining living organisms, allowing them to work efficiently, to utilize resources and respond to environmental changes. Now coming on to the entropy consideration in case of these biological systems. They often manage entropy through complex mechanisms to maintain the different biological process. While the individual reactions may increase entropy, organisms employ the various strategies to regulate their internal environments. Okay. Now, therefore, these biological and chemical processes are predominantly characterized by irreversibility, reflecting the natural tendencies of energy transformations and entropy changes. Understanding this process is very much essential for grasping how living systems operate and adapt to their environment.